Dear students, you are most welcome in this class. We continue with the same topic, same subject, and just I will flash the slides where we started yesterday. You have seen that first we fitted the equation, we have found out value of A and B. Then we tested it for linearity, whether the equation is linear or not. In the third step, we have fitted or we have plotted the equation. And you have seen that R square is also mentioned here. Then we discussed the characteristics of a graphical representation, these characteristics, and then we computed the coefficient of correlation and tested its significance. And then we wanted to learn more on determination, coefficient of determination, R square. So these were explained to you. Characteristics of R, correlation coefficients, and requirement for testing the significance of correlation coefficient. We discussed the formula of correlation coefficient, and you can see the major step. Fitting the equation, testing.
Your slide is not visible, sir.
Oh, okay. So I think I made it in a full mode. Therefore, it was not visible. Now, can you see it now?
Yes, sir.
Okay. So is it seen? You can read the lines because text becomes smaller when we do it. Otherwise, I will continue with this bit. Okay. So you have seen the fitting the linear equation, computation of value of A and B, and then testing the significance of the linear equation. Next step, and followed by plotting the linear response curve. You see y min and y max values were computed by putting the respective values of the x, and you can plot it like this. And characteristics of the graphical representation of the linear equation, and then computation of coefficient of correlation and R square. You have seen all these. Testing the significance of R correlation coefficient. I told you t-test and that Fisher table. We call it Fisher correlation coefficient tables. So two methods were discussed. You have seen this table. This is correlation coefficient table. And we have seen the inferences based upon the correlation coefficient. So you can square the correlation coefficient and multiply it by 100. Whatever you get, that much of variation can be explained by the linear relationship between two variables, 98.2%. Higher the value of coefficient of determination, better is the fit. Suppose it is 1, R square is equal to 1. It's 100%. The points are, the line is passing exactly from the points. That means there is no error. There is no error. That is the best fit. So just now we go to the coefficient of determination. Today your class starts from here, coefficient of determination. Just I want to show you in the table how you can know or what is coefficient of determination. Now you see this table. This table, first column is sources of variation. There are two sources. Linear, you can consider it as regression. Regression, sometimes I use them interchangeably, but it is regression. So regression and residual. Residual is your error. So if your error values of sum of square are low or very low, then you will have higher values of the regression, sum of square. So actually R square is the proportion of sum of square due to regression and total sum of square. So total sum of square is 6.38, out of which the regression sum of square is 6.27. If we increase the value of, if we keep the total sum of square fixed, just keep it fixed. And then if we increase the value of the regression sum of square, then the R square value will increase. So if you have less and less, if your error sum of square is 0, then you will have R square as 1. R square as 1, because this will also be 6.38. Suppose this is 6.38 and residual is 0, then total will also be 6.38. That means in that case, you will get value of R square as 1. So here, I think the coefficient of determination is the ratio of the sum of square due to regression divided by total sum of square. So I will try again to make it in full mode, and then you can see if slides are moving or not. Just tell me whether the slides are moving or not. I moved it. Can you see the moved slide?
Sir.
Is it visible to you? Moving
No,
slide?
sir.
No? I'm moving the slide. Can you see
सर
the...
स्लाइड ही सर विजिबल नहीं है.
Okay. Now?
हाँ सर.
Okay.
Now it is okay, sir.
Fine. Now we go to the coefficient of determination. So you can see the definition. It is the sum of squares due to regression when expressed as a proportion of the total sum of square. Please do remember this is the meaning of coefficient of determination. Not much big problem. You can easily understand. Coefficient of determination is the sum of square of due to regression divided by total sum of square. Or you can say it measures the amount of variation in y accounted by the variation in x. Or you can say R square indicates the proportion of the variation in the dependent variable that has been explained by the model. For the present example, R square is, and furthermore, if you have computed R square, you can take the under root to find out the coefficient of correlation and vice versa. So you can see coefficient of determination, that is R square, SSR, sum of square due to regression divided by total sum of square. So you get 6.27 divided by 6.38. This is 0.982 is your coefficient of determination. If you take under root of this value, it will be coefficient of correlation. The value of R square is the proportion of the variation in y that is explained by the linear association between x and y. The value of R square quantifies the goodness of fit. Goodness of fit, how fit the equation is, means it has the least, lowest residual sum of square or lowest error sum of square. Now remember, correlation coefficient values vary from -1 to +1, but coefficient of determination values vary between 0 to +1, and it has no unit. Similarly, correlation coefficient has no unit. Higher value indicate that curve comes closer to the data, means your curve is a better fit. Statisticians use uppercase for the result of non-linear and multiple regressions and lowercase for the result of linear regression. But this is distinction without a difference. Means it does not matter whether you are using capital R square or small r square. They are conveying the same message. When R square equals to 0, sometimes it can be 0 also, the best fit curve fits the data no better than a horizontal line. So it will be a horizontal line if you have R square 0. Or if it is a horizontal line, then R square will be 0. Horizontal line going through the mean of all y values. In this case, knowing x denotes no help, not help you predict y. Means it is a very loose fit or it is not a fit at all. When R square is 1, highest value, all points lie exactly on the curve. All original points lie exactly on the curve with no scatter. There is no scatter at all. If we know x, we can even calculate y exactly. We can think of R square as the fraction of the total variance of y that is explained by the model. So these are different explanations for coefficient of determination. only R square is not the main criteria for whether a fit is reasonable. A high R square tells us that the curve came very close to the points, but does not tell that the fit is sensible in other ways. So this is for a statistician to understand, but our job is over what is coefficient of determination. Now, overall, you have seen different steps in response curve fitting. Again, I repeat here, fitting the equation, testing the significance for linearity, plotting the equation, correlation analysis, and then computation of coefficient of determination. And the fifth and final step is residual analysis. So this residual analysis is beyond the scope of this course, but this is also very, very important. So what you can do, you have original values, say 0, 40, 0, 40, 80, 120 for nitrogen. These are X values. Similarly, you also got corresponding Y values. For these two, independent and dependent variable, you have fitted an equation. Now you have found out an equation and which is also significant, which is also linear. Now what you can do for respective values of independent variable, that is 0, 40, 80, 120, you can make you can calculate the predicted values from the equation. First time you can put value of x 0 in the equation, y is equal to a plus bx. Then you can put 40, you will find some estimated value of y. Similarly, for 80, you will find some estimated value of y. Similarly, for 120, you will find estimated value of y. So now you have two columns. In one column, you have original value of y. In second column, you have expected or estimated value of y, dependent variable. Now you difference these two, capital Y0, small y0. You take the difference of these two. These differences will be your residuals. These differences will be your residuals. And then a lot of statistics is involved on residual analysis. Residual plots are there. And even the significance of residual values is also tested. Again, F test come into picture. So ये कभी पीछा नहीं छोड़ते statistician. Residual का भी F test कर देते हैं. So there is big statistics beyond this. So I'm not going into residual analysis, but many people are writing papers based upon these residual values. They again go for regression analysis. One side they will have original value, and on another side they will have residual value, and go for further statistics. So that is not desirable here. But I understand that you know that what is residual. So if you take the total of residual values, that will be 0 if your equation is significant. So I hope that you know what is residual. Now, any question at this point of time? No question. Okay. So we go to the next kind of relationship, which is non-linear or curvilinear relationship. So first you have seen linear, now we see curvilinear, which is a kind of polynomial relationship, starting with quadratic, cubic, and so on. The relation between variable when the regression equation is non-linear, that is quadratic, cubic, or higher order, is called the curvilinear or polynomial relationship. So you can see that in curvilinear, the linear word is hidden. Means it is partly linear and partly in the form of curve. Therefore, it is called curvilinear. And non-linear means it is not linear throughout. It is not linear throughout. It is a form of linear regression in which the relationship between the independent variable x and the dependent variable y is modeled as the nth order polynomial. The curvilinear relationship among variables is quite common in biological organisms, including crops. So you have seen law of diminishing return kind of things. Those are all curvilinear kind of relationship. The response to a variable is rapid at the beginning. You have seen your marginal return was increasing. slower at the intermediate levels, marginal return started falling and could even become negative at high level of the variable. So such kind of relationship are curvilinear relationship. The pattern of plant growth over time, which usually starts slowly, increases to a fast rate at intermediate growth stage and slows down towards the end of the life cycle. You have seen sigmoid curve, so that is also a curvilinear relationship. Curvilinear relationship is a polynomial type of relationship, except the linear relationship. The first order, the regression models or equation of polynomial type having curvilinear, these are already shown to you. Y is equal to a plus bx plus cx square, cubic a plus bx plus cx square plus dx cube, and so on. Similarly, nth degree, you can write in place of a, you can write b0 also. In some statistics book for intercept, they can write b0. And then b1, b2, b3, b4, along with the polynomials, 1, 2, 3, 4, 5. So this is your nth degree polynomial. Now, we are going for response curve fitting. Few minutes back, we have finished linear response curve fitting. Now we will see curvilinear response curve fitting. In this case, we are taking quadratic example. Y is equal to a plus bx plus cx square. Quadratic response. So in this case, what we are going to do, we are going to follow exactly the same steps. Same steps what we did in linear relationship. Fit the quadratic equation means you need to find out value of A, B, and C here. Here you have two regression coefficient, B and C. Then you will fit the equation, you will find out the equation. Then you will test the significance, whether it is curvilinear or it is linear. What kind of relationship it is having. For your kind information, if your test, first you need to test it for linearity. If your linearity test is significant, that is AND. But if the linearity test is non-significant, means your equation is not linear equation, then you can go for higher order testing, means test the significance for quadratic equation. So test the significance of curvilinearity. Then third is plotting the quadratic response curve, making a graph. Fourth is computation of correlation coefficient and coefficient of determination. And you can test the significance of the correlation coefficient and then inferences of R square. And once you have done up to step 6, the additional step could be computation of optimum economic dose. From linear relationship, you cannot find out the optimum dose of the fertilizer because with every unit, the return is same. With the increase in every unit, the return is same or constant. So there we cannot decide the optimum economic dose of fertilizer. So here, what is the problem? That you have a curvilinear kind of relationship. So it is not a straight line. So if it is not a straight line, then it is very, very tough to identify the coordinates. Because it is curvilinear. It is in the form of a curve. It is not a straight line. So what is required? Statisticians suggest that first you straighten this line, convert this curve into a straight line by some relationship, by some statistical procedures. This curvilinear or this curve can be converted into a straight line. And once this straight line is made, or linear relationship is made out of curvilinear relationship, then you can solve the equation. Then you can find out the values of A, B, and C. So how to solve the quadratic equation, we will see it. So the response to fertilizer, for example, plant population, irrigation, other inputs can be quadratic relationship. And you can work out the economics. In case of fertilizer, usually the response is quadratic. Based upon experimentation in the past, people have confirmed that response to fertilizer is mostly a quadratic response under normal conditions. Before fitting such response equation, it is necessary to ascertain that the treatment variable have a significant effect on the dependent variable. already told in case of linear relationship that your response variable should be significant. F test should be significant, then you can go for correlation and regression analysis or fitting a quadratic response equation. The fitting of quadratic equation is shown below with a hypothetical example. I'm showing you one hypothetical example, and then you will learn how to fit a quadratic response equation. How to fit means to find out value of A, B, and C. Fit a quadratic equation from the data given in the following table and calculate the optimum economic dose of the K2O of potassium when the cost of 1 kg K2O is ₹10 and price of 1 quintal rice is ₹500. So this is the problem you need to solve. And this problem I have taken exactly from Gomez and Gomez book. In Gomez and Gomez book, you have one chapter on this kind of subject, correlation and regression analysis. And I have already shared that chapter to you. So you can see, read from that chapter also. So you can see here that you have the data, you have values of X, that is 0, 30, 60, 90, 120. And you have value of dependent variable, that is Y, at respective independent variable at 0, 4, 8, 7, 8, at 30, 60. So you are seeing these values. And now the first job is to fit the equation to find out the value of ABC. So how to do it? You can see it. It is very simple to understand, not a tough job. Now you have column number 1. Here it is X, the levels of potassium, K2O, per hectare in kilograms. So you have 0, 30, 60, 90, 120. So you can see here, it is actually X. But as I told you that the equation has been converted, the curve has been converted into a straight line with some relationship. So therefore, a new variable was created, that is Z1, capital Z1. That is exactly your X. X means X is now written as capital Z1. This is your independent variable. So then you see column number 2. This is Y. This is dependent variable, grain yield kg per hectare. Okay. So these two columns are clear to you. One is X, which is equivalent to Z1, capital Z1. Number 2 is your Y, the same dependent variable. And number 3 is Z2. It is another variable, which is X square, which is equivalent to X square. Here it is quadratic relationship. So square is made for column number 1. And the variable has been named as capital Z2. For further details, how this transformation was done, I suggest you to see the chapter by Gomez and Gomez on correlation and regression analysis. It is explained in detail how these variables were linearized. So here just I am teaching you how to do it actually. And I'm not able to explain you theory behind it because some statistical theory is there that has converted this variable into X square. So for the time being, you see Z1 is X and Z2 is your X square. So if you square the column number 1, you get X square, which is capital Z2. And you can square 900, 3600, 8100, so on. And you can take the total of this, which will be summation X square or summation Z2, summation Z2, capital Z2. And in the same way, in the column 1, you can take the mean of Z1. Z1 bar, you can calculate. Then Y bar, you can calculate. So now you need to create several variables, sum of squares, which are given in column number 4 to 12. So you need to compute these kind of variables, these kind of corrected sum of square to compute the value of A, B, C. And they are very simple. I explain you. So up to column number 3, you are clear. Now see column number 4. It is small z1. Small z1 means capital Z1 minus Z1 bar. So this is related to column number 1. So you take the mean of this, which is 60. So 0 minus 60, you get minus 60. The 30 minus 60, you get minus 30. Likewise, you get rest of the values. So sum of the Z1, sum of the small z1 is 0. Therefore, you need to square it. Small z1 is square. And you square the column number 4, you will get the column number 5. 60 into 60, you get 3600. 30 into 30, 900. Now, next difference is or Z2 minus Z2 bar. This is capital. And you calculate small z2. Small z2 means Z2 minus Z2 bar. So you know about Z2, column number 3 is Z2. You take the mean of this. Whatever mean is there for Z2 mean, Z1, Y1, Z, 5400. So 5400 is the mean of Z2 here, 5400. So you can take this column number 3, 0 minus 5400, you get minus 5400. 0 or 900 minus 5400, you get minus 4500. 3600 minus 5400, you get minus 1800. So likewise, you will get different values, different deviations against the mean for capital Z2. Now you need to square it. So column number 6 can be squared. Every value can be squared to get the column number 7. Z2 square. Now comes the small y minus y bar. So you can take the mean of y. Mean of y, you can see here, it is 5824. 5824, mean of y. So y minus y bar. The column number 2 is y. So from all the values, respective values, you deduct the mean of y and you will get this value, this column number 8. Is it clear up to now? Okay, now we go for y square, small y square, and then square the column number 8, square the values, you get small y square, and here you can take the total sum. That will be summation y square, summation small y square. Similarly here, summation z2 square you can calculate. And now the next, corrected sum of square is summation small z1 y. So you can see small z1 is column number 4 and capital Y is column number 2. So you multiply these column, small z1 and capital Y columns, and you get these values. Next is 11 number, summation z2y. Small z2 is your column number 6 and capital Y is your column number 2. So multiply column number 6 by 2, you get these values. The final 12th column is small z1, small z2. So there you have one column small z1 and another column small z2. So multiply these two, you get column number 12. And take the sum, take the total. Here also you can take the summation small z2 capital Y, small z1 capital Y, summation y square, summation z2 square, and summation z1 square, and mean of column 1, column 2, and column 3. If you have all these weapons in your armory, you can solve the problem or you can kill the enemy. Now you see here, mean of x is 60, mean of y is 5824, and mean of z2, that is x square, is 5400. So these three values were computed. Similarly, now you need to compute the corrected sum of squares, and you have seen in the last table, these values were computed. Small z1 square, summation z2 square, summation y square, and so on. So from the above table, for our example, the linearized form of the second degree polynomial quadratic equation is y is equal to a plus bx. So in place of x, it is z1. It is z1, capital Z1 plus cz2. Actually, it is x square. So x square has been made equivalent to z2, capital Z2. So that square was linearized. So this is the form of the equation with some relationship of z1 with x and z2 with x square. So now equation can be solved. where two newly created variables Z1 and Z2 are defined as X and X square. I do not know beyond this point about how these variables were transformed, but this is how we do it. In ISRE, whenever you get a chance, you can learn there how these variables X and X square were transformed into Z1 and Z2 so that your equation is linearized. And we linearize this equation to solve the equation because we cannot directly solve the quadratic equation. Now it is a quite complicated formula. You can see regression coefficient is B here is equal to summation Z2 square summation Z1Y minus this, and you can see, and these all have been calculated on the last slide, if you remember, and you can put the values of respective sum of squares here. You see, and you get value of B as 26.646. This is the value of B. Now, value of C also summation Z1 square summation Z2Y minus so, and you get value of C also. By chance, the value of C comes in minus. So you can see here how to compute the value of B and C. At least you got some idea how to work out the value of B and C. Formulas are complicated. You need not to remember all these, but procedure, steps, you should remember. So whenever required, you can take formula from the book and solve your equation. So this is how we get value of B and C. Now value of A we can obtain by difference Y bar minus B Z1 bar minus C Z2 bar. You know the value of Z1 bar, you know the value of Z2 bar, mean. And you have just now you have calculated value of B and C in the last case. And then you can put the value here. So Y bar, mean of Y was 5824 minus value of B you computed in the last 26.646. This is the value of B. And Z1 bar, mean of X or Z1 was 60 minus within bracket value of C was in minus. So minus 0.1178. You see last you have value of C 0.1178. So here you can see you can calculate the value of A, which is your intercept, and you put the value of Y bar here. So minus B Z1, Z2, I think. And then you find that your A or intercept is 4861.66. So value of A is 4861.66. Value of B, 26.646. Value of C is minus 0.1178. So thus the second degree polynomial regression equation describing the yield response of rice to the potassium fertilization within the range of 0 to 120 kg K2O per hectare is estimated as Y is equal to 4861.66 plus 26.646 X and minus 0.1178 X square. Remember, in the equation, it is always plus. But when you solve the equation, value may come out in minus. Therefore, now you see minus in the equation. Otherwise, equation is always positive equation. Every term in the equation is positive. Now, computation of the coefficient of determination, capital R square. Here, R square is equal to B Z Z1Y plus C Z2Y divided by summation Y square. So these are the terms you need to enter. You have already computed these terms in the table. Put the respective values and you get R square as 0.996. Now, now you have calculated the value of R square also. So you can explain what is meaning of 0.996 R square. I will explain, don't worry. But for the time being, now you test whether it is a quadratic equation or not, like you tested a linear equation. So here also you need to put F test. So there, in case of linear response, test was very simple. But here, the formula is quite complicated. You just see how complicated this formula is. Anyway, F is equal to N minus K minus 1, B summation Z1Y plus C summation Z2Y as a numerator. And in the denominator part, you see K, small k, summation Y square minus B summation Z1Y minus C Z summation Z2 by. So this is formula to compute the F test or Fisher test. And C N is the number of observations. So number of pair of observations. So here number of pairs were 5. So you put here 5. And then K is number of variables linearized. So in this case, 2 variables were linearized. One was X, other was X square. Therefore, 2 variables were linearized. So therefore 2 minus 1. And then next you can put the values of these terms and you get F calculated as 245.32. And if you see the value at F value, table value of F at, you can see how many degrees of freedom. You can see error degree of freedom means regression degree of freedom and error degree of freedom means 1 and 2 or 1 and 2, 1 and 2 degrees of freedom. Because the computed F value exceeds the tabular F value with F1 is equal to F2 is equal to 2. So here regression degree of freedom. You have 2 sources, one is regression, other is error. So for regression, it is always 2 here. Degrees of freedom, as I told you, for linear relationship, regression degree of freedom is 1. For quadratic, it is 2. For cubic, it is 3. So regression degree of freedom is 2. And for error, it is n minus 2. So for error, it is n minus 2. So how many n's were there? 1, 2, 3, 4, 5. So 5 minus 1 is total degree of freedom is 4. So you get n minus 2, that is your 2 degrees of freedom.
Sir, here degree of freedom will be n minus 2, na total degree of freedom.
Yes. The total degree of freedom will be 3. Total,
yes,
yes, total degree of freedom will be 3. Just a minute. Where it has gone here? Sorry. Yes. See, I take back to see here we have 1, 2, 3, 4, 5. 5 pairs. So total degree of freedom is n minus 1. So it will be n is your 5. 5 minus 1 is equal to 4. And that n may be wrong also. That n may be wrong also. Because total degree of freedom here will be 4. First thing. Second thing, your regression, for regression, it is fixed. For regression, it is 2. So for error, it is total degree of freedom minus 2. Minus 2. Otherwise, you need to keep it n minus 3. Because n is 5 and then minus 3, then you will get 2. Okay, so it is by difference. Is it clear now? I make it more clear to you. Now you can see this. In this case, there were 4 observations. There were 4 observations. So total degree of freedom is 4 minus 1 means 3. And for linear, I told you it is always 1. So for residuals, it is very simple. 3 minus 1 is equal to 2. Similarly, in that case, you forget for the timing n minus 2, n minus 1. Here you see the total degree of freedom will be 4 because it is n minus 1. So it will be 4. And for quadratic, when your response is quadratic, you have 2. For regression, you need to have fixed degree of freedom, that is 2. So 4 minus 2 is equal to 2. 2 for residual. So here degree of freedom is 2 for both. It is 2 for n minus 2 may be true for linear case, but here, because there the degree of freedom for regression was 1. Here it is F1 is also 2 and F2 is also 2. So in the first row, in the horizontal column, you need to see at 2 degree of freedom. Similarly, then on vertical column at 2 degree of freedom. You will get the value of F and you compare it with the table value of, with the calculated value of F. If your calculated value of F is more than table value at 1% or 5% level of significance, then it is significant, otherwise it is not. So in this case, it was significant. You can see the last year, at 1% level of significance, you have 99 values of a table value of F at 2 and 2 degrees of freedom. So which is much less than the calculated value. Therefore, it is significant even at 1%. If a value is significant at 1%, it is surely significant at higher level of significance, at 2%, 5%. If it is significant at 1, that means it is significant at all higher levels. Now, you see the explanation. You have also seen the R square is 0.996. You multiply it by 100, you get 99.6. That means 99.6% variability in the data has been explained by the linear function of x and y. So that is the explanation. Because the computed F value exceeds the tabular F value at 2 and 2 degrees of freedom, the estimated quadratic regression equation is significant at 1% level of significance. Now, what we can draw inferences, further inferences, yield response of rise to K2O fertilization can be adequately described by the quadratic equation. Means it is following a quadratic pattern. The fertilization of K in rice is following a quadratic pattern in this particular case. Now, R square is 0.996 indicates that 99.6% of the total variation in mean yields was explained by the quadratic regression equation estimated. Quadratic, sorry, that was not linear. I did mistake last time in explaining it. I could have said it is quadratic regression equation in place of linear regression equation. So I hope that this is clear to you. The rate, so these are the inferences. Now your this part is complete. Fitting the quadratic equation is also over, and you have also tested its quadratic nature. You have confirmed that it is a quadratic equation by having the F test. So you have also calculated the value of R square, from which you can also calculate the value of correlation coefficient, take the under root of R square, and then you can also see the significance of correlation coefficient in the fashion you did it for linear relationship. So any question, any doubt up to now? I will try to answer. Yes? No. So do you think it is a tough subject or it is interesting subject? Sneha. Sneha, do you think it is tough subject or it is interesting subject? This correlation and regression analysis. Are you listening to me? Or there are two Sneha. One is Sneha Bhardwaj, other is Sneha R. Sneha R, are you there? Sneha R. Hello. Pachappa?
Yes, sir.
Yeah. So do you find it interesting or do you think that it is a bit tough?
Sir, little bit tough, sir.
Okay. So actually I tried to inject some interest in you on this subject.
Yes, sir.
But rest is in your hands, how much you are interested. But one thing I tell you that this is the most very, very important subject for you to understand. In your life, wherever you will go, whether you become a businessman, whether you become a scientist, a teacher, or in any service, wherever you live, even as a farmer, whatsoever, wherever you go, this subject is applicable everywhere. This is applicable in science, in art, in literature, everything. This is applicable. And it is only thing is that if you have knowledge, how I can make use of this knowledge. And this is very, very important. People who are doing MBA, Masters, Business, Economics, for them, this is very, very practical subject. So each one of you should have sufficient idea about this subject. In agriculture, in crop production, in soil science, in agronomy, nobody can succeed without knowing it. Even soil scientists, when they develop some test, testing the nutrients, making soil tests, different kind of test, they cannot recommend those tests without sufficient regression analysis. A lot of statistics is used before recommending any test, soil test. So this is very, very useful subject. Now, one usefulness I show you in the determination of the optimum economic dose of the fertilizer. So what is optimum economic dose of fertilizer? Rate which produces maximum economic return. Where you get maximum money from the unit or input or fertilizer, money invested on the input. Optimum economic dose of fertilizer can be determined if the response is quadratic. Only in case of quadratic response, you can determine the optimum economic dose. You cannot do so if your relationship is linear. In case of linear response, OED cannot be worked out. As a rule of thumb, optimal rate determined on an economic basis are smaller than those required to produce maximum crop yields. So as you know, as you go on increasing the levels of fertilizer, any fertilizer, NPK, calcium, magnesium, as you increase the doses of the fertilizer, the yield increases and it will continue to increase, and the fertilizer level where you get maximum yields is the highest quantity of fertilizer that is giving you response. However, that response may not be economic. That response may not be economic. The economic levels may be much higher than the levels which give you maximum yields. So normally those levels are 80% of the maximum level of fertilizer, where you get maximum yield. So optimal rates are lower than the maximum yield rates. So economic yield targets usually do not exceed 80%, generally 80% of the maximum potential yield. Suppose you are getting maximum potential yield at 120 kg, suppose, or say 130 kg, you are getting the maximum yield, but that may not be economic. So normally people have conducted several experiments and they say roughly it is 80% of the maximum yield dose. maximum yield dose. The dose where you get maximum yield is your maximum yield dose. So normally optimum economic dose is 80% of the maximum yield dose. Suppose maximum yield dose is 130, then 80% means how much? 130 by 80%. Hello? Navneet, what is 80% of 130?
Sir, 104.
Okay. Are you not sure? Karo isko, do
Yes.
it. Okay. If it is 102, means you have gone up to 130 kg, but your economic rate has come out to be 102. So this is very general, very vague idea, 80% based upon several trials people have made. But the real figure, the actual figure, we need to work out from by fitting the equation, conducting the experiment and fitting the equations. So it does not include economic variables such as fixed cost associated with fertilizer use or interest rate to be paid on loans for purchasing fertilizer. So actually it is just concerned with the fertilizer, one particular fertilizer. It is not taking into account the total economics because there may be other costs of cultivation also. It is one variable, there can be several variables. So it is just restricted only to the fertilizer.
Hello, sir.
Yes, yes.
Sir, I have a doubt regarding this. It is 80% of maximum yield or maximum fertilizer applied?
It is from the fertilizer applied. I told you it is maximum yield dose. 80% of the maximum yield dose. Maximum yield dose means the value of X or value of fertilizer where you get maximum yield. So this is maximum yield dose. This is for the dose.
Okay, sir. Thank you, sir.
Okay. Now, from the quadratic equation y is equal to a plus bx plus cx square, the optimum economic dose can be worked out. OED, you can write it optimum economic dose or optimum dose only. Even sometimes you can write optimum dose. Optimum dose means it is understood it is optimum economic dose. Or sometimes people write economic optimum dose. EOD or OED. So you can write both ways, both are correct, either economic optimum dose or optimum economic dose. So formula is Q upon P minus B whole divided by 2C. P and C are the regression coefficients. You have fitted the equation and you remember you have found out the value of A, B and C. So you can put the value of A, B, C and P is the price, Q is the cost of 1 unit of fertilizer or input, and P is the price of 1 unit of output. So this is formula you need to remember, and you will get one numerical on this. So better to remember this formula. And if you see the numerical where we started, this. So here you see fit a quadratic equation from the data given in the following table and calculate the optimum economic dose. When now the price and cost is given to you. Cost of 1 kg K2O is rupees 10. So 1 kg K2O is rupees 10. Okay, so it is easy. 1 unit price of input is 10. And price of 1 quintal of rice is rupees 500. So here you can see price is given for 1 quintal. But your data is in kilograms. You see, the data is in kilogram. So now you need to write P or price in kilogram. So 1 quintal means 100 kilograms. So price of 100 kilogram is 500. So price of 1 kilogram rice which you are selling is rupees 5. If in your equation in your data, suppose this is your data, if this data is given in tons, if you convert this data in tons, say 4.878 tons, 5.506 tons, 6.083 tons, and so on. So if the data is in tons, then you need to consider price also in tons. So now if you have 5 rupees for 1 kg, then it will be 5,000 rupees for 1 ton. So you must see the units in the example given to you. Whatever units are given in your example, you need to take unit price of that. If it is kilogram, kg, K2O per hectare, then you take price of 1 kilogram. Here also grain yield is in kilogram per hectare. Then take price, in the first case it was cost. Here take the price of 1 kilogram of rice. Okay, so sometimes the examiner, the person asking question may confuse you. So here it is price of 1 quintal here. However, in the equation, you see data is given in kilogram. So you need to convert, otherwise you can convert it in quintals also. You can convert it in quintals also, then go fine. So remember these things, these are the points. So now you should be aware of this OED Q upon P minus B upon 2C. And now you need to work out the maximum yield dose. What somebody was asking you. So this is maximum yield dose. This is estimated. This is estimated. This is not the actual. Actual you can see in the table where you are getting maximum yields. Again, I can go back. I can go back to the example and you can see here. So here 120 is the maximum yield dose. 120 is the maximum yield dose where you are getting maximum yield. But this dose may not be optimal. This dose may not be optimal. So here you need to calculate the maximum yield dose. And that was the original maximum yield dose. Now based upon the equation, you can also work out, calculate the maximum yield dose, which is, in short, you can write X max. So it is very easy to remember, minus B upon 2C. Put the value of B and C in the equation and you get 113.09. So theoretically you were getting, or originally you were getting 120 maximum yield at 120. But here you are getting maximum yield at 113 based upon the fitted equation. Now optimum economic dose is Q upon P minus B upon 2C. Q is the cost of 1 unit of fertilizer. Cost, Q is cost. So 1 kg of K2O was for rupees 10. You put 10 here. Divided by 5. 5 is the price of 1 kg rice. Bracket close. Minus B. You can put the value of B. Divided by 2C. 2 into C value is minus 0.1178. So therefore, you get 104.6 kg per hectare as optimum economic dose. So you can see that if you see in practical sense, your maximum yield dose was 120 kg. But economic returns you will get at 104.6 kg K2O per hectare. So this is the optimum economic dose where you will get maximum returns. Now, there are some further calculations for the students. Sometimes they are asked in exams, what is response? So response with respect to fertilizer at optimum dose. Response at optimum dose is equal to yield at optimum dose minus yield at control. This is the formula you need to remember. So how much you are getting at optimum dose and yield at control. So you can calculate the yield at control by fit. You have the equation y is equal to a plus bx plus cx square, where you got values of b, c, and a also. Just put the value of x. So you will get value of y for respective x. So similarly, put the value of x in the equation, 104.6 in the equation, and 0 for control in the response equation. So at 104.6, the predicted yield will be 6359.96, and this will be for control. And for 104, it is 6359. So now response at optimum dose is equal to 6359 means yield at 104 minus yield at control. So now you can see 1498.3 means this much of additional grain you are getting because of K2O application at optimum dose of K2O. This much is extra, this much is additional. So actually this is response, means yield in the treated plot or yield at optimum dose minus yield at control. This is your response. Now you can go do further calculation, response in kg per kg K2O. So it is response at optimum dose, kg per hectare. This is this much, 1498, and divided by the optimum dose. So you get response in kg per kg K2O. 1498.3 divided by 104. So you get 14.32 kilogram of grain per kg of K2. This is how we are calculating response, and response ratios you must be listening, and you must be listening that declining response to fertilizers were very common. So this is the response which is declining, means 1 kg K2O is yielding less and less with the passage of time. With the time, we are getting less and less response to fertilizers. Now we continue. Now you see, if you want to calculate the profit for hectare basis, then value of the produced rupees per hectare minus cost of K2O per hectare. So value of produce here means the additional produce. So value of produced rupees per hectare is equal to response at optimum dose, how much additional grain you are getting, and selling price, what is the rate? Selling price. So cost of K2O, how much K2O was applied for getting optimum return, maximum return? It was 104.6. 104.6. So 104.6 will give you 1498.3 extra gain. This was the response, and rate is rupees 5 a kg. So this is your return minus 10. 10 is the price of 1 kg of K2O into 104. So you get this much per hectare of return because of application of optimum dose of fertilizer. I repeat it again. Profit is equal to value of produce minus cost of K2. So value of produce rupees per hectare is equal to response at optimum dose. You have calculated response as 1498 into selling price is rupees 5 for rice. Cost of K2O per hectare is cost of 1 kg K2O and optimum dose, total quantity of K2O applied. So this is 104.6. The price of 1 kg K2O is 10. So this is your input, this is your output, additional output. You get rupees 6,445.5 per hectare returns due to K2O application, 104.6 kg K2O application. And further economics is return in rupees per rupee invested on K2O. This is formalized profit per hectare divided by cost of K2O per hectare. So you can divide it and you find 6.16. So here, if you invest rupees 1 on fertilizer K fertilizer, you get 6 rupees or 6.16 rupees additionally. So last slide is uses of response curve, interpolation. Interpolation means you have some say doses from 0 to 120. So you can calculate the response for any dose. Response for say 65, you can calculate. Response for 92, you can calculate. Interpretation, several interpretation can be made. The relative response to different sources of nutrient can be seen. Different doses, you can see the relative response. Economic response, just now you have seen. To find out the economic optimum dose, to increase the efficiency with which farm resources are used, to provide guideline to the individual. So there are many uses, and many uses I will discuss in the next lecture. What are the uses of response curves? There are a number of uses of response curves. And that ends your lecture. Now your questions are welcome. You can ask questions, clarification, comments, and whatever you want.
Hello, sir.
Yes.
Sir, by this equation, how can we calculate the relative response of other fertilizers?
Relative response.
Point number 3.
Yes. See, relative response, what we can do, many times we can take two sources of the fertilizer. Suppose we can conduct one experiment where we can have two sources of fertilizer, and we can have level, we can have same, say 0, 40, 80, 120, 160. These are the levels. And suppose we want to compare whether ammonium sulfate is more effective or urea is more effective. Okay, so we will give nitrogen from both the sources. We will give 40 kg from both sources, 80 kg, 120, 160 kg. Okay, same quantity of nitrogen will be supplied through two different sources. And we will record the yield for source 1, yield for source 2. Okay, now we will have two columns of the yield. So we will, in one curve, in one graph, we can plot two lines, isn't it? Two different lines. We need not to merge these lines, and then we can do the economic analysis. See, response curve can be fitted for source 1, source 2 separately in one graph. It is possible. Is it not clear? And then you will have two different lines, and these are response lines, and you can see which line is giving you more economic return for line 1, for line 2. Similarly, you can have varieties also under one, or you can go for multiple regression also. Otherwise, a simple way is to I'll show you tomorrow, I think. This question I keep pending, and tomorrow I will start from this point. I will show you tomorrow how many variables can be plotted on one graph, one chart. For example, this response you have recorded, not just, you can vary the input. Here there will be two different variables, two different sources, or two or three varieties. Even you can have 4 varieties and see the response to levels of nitrogen. And you will have 4 or 5 different lines for varieties, variety 1, variety 2, variety 3. Similarly, you can have dependent variables also, many dependent variables in one picture. So one graph, that is, suppose your yield, grain yield is dependent variable. So is your nitrogen uptake is also dependent variable. Your straw yield yield is also dependent variable. So 3 dependent variable can be plotted on one equation influenced by one independent variable. So it is possible, and on the same graph you can compare 2 equations, 3 equations, 4 equations, 5 equations. So this subject I will definitely discuss tomorrow morning if I take your class. Is it okay?
Okay, sir.
Not clear? अरे नहीं हो तो बता दो, मैं बता दूंगा. I will tell you. But
नहीं सर, क्लियर हुआ है सर.
कुछ क्लियर हुआ है, कुछ कल मैं सुबह करूंगा.
हाँ सर, कल बाकी देख लेंगे सर.
You can do one thing. I have given you 3 presentation on uses of response curve. And if you start seeing the third presentation from the starting 4, 5, 6, 7 slides, I think those slides you will find answer to your question. Just try to see those slides, and again I will discuss it. So any other question from you or any other student?
Sir, in this case, in this quadratic equation, we have converted it into linear and make the values of all the things in linear. Then when we will plot this, the curve will be linear, na?
Oh yes, curve will be linear. Curve will be linear.
Okay,
100%. 100%. So that is actually my weak part. That is some complicated subject. So I could not study that part, but in ISRE people can teach you that part. So I just told you mostly the applied aspect of the thing. The theoretical part is in ISRE, I think. Okay. So I see that from 11 students, now how many are there? 21. That is nice, good attendance. So I can take your attendance. You can show your faces, please. So thank you very much. See you tomorrow at 9:15. If I am not there, Dr. Divakar may take your class. If I am there, I will take your class. Control P. Okay. Thank you very much. Bye. And if you
Thank you,
want,
sir.
if you want message, I can give you one message today also. Have cooperation with each other. Cooperation with each other means if you are living in same area, in one particular area, or if you are close to each other, then become your own teacher. Suppose you are 2 people, 3 people, and do group study. Group study is really good. If you are in touch, or if you are even not in touch, 2 people, 3 people, 4 people can make a group and decide the topic. Okay, Arijit will learn cultivation of chickpea. Shalini will learn cultivation of lentil, or Satyapal will learn cultivation of mustard. So suppose you are 4 in a group, you will learn 4 different chapters, and one by one will teach the other 3. One will teach the other 3, and that way the all 4 will be benefited. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.